we're going to have a look at daily atmosphere, and in particular, we're going to have a look at the methods you can use, experimental methods you can use to calculate the percentage of oxygen in the air and why they don't always work. So let's just have a quick look at what our air is made of. And often we think of our air as oxygen. And actually, funnily enough, in the exams, if they ever say something is reacted in air, what they're talking about is that object is reacted with oxygen. So there is kind of a misconception there. However, air is mostly nitrogen. So about 78% of our air is nitrogen. In the exams, they tend to put it as 80%, but it is about 78%. Oxygen is just under 21%. Again, in the exams, they say 20%. The numbers are just easier, but it is about 21%. Now, the rest of the air is made up of a number of different gases. Most of them are noble gases. So this is noble gas, noble gas, noble gas, noble gas. They don't really do very much, just like nitrogen. The reason we don't notice nitrogen's there is because it's got a triple bond. It doesn't react very much. It doesn't react easily with anything. And the only things that can really cause it to become something useful and actually react is lightning and certain bacteria, often found in pea plants. Now, if you have a look, you've also got a very small proportion of carbon dioxide and methane, and these come up in the news quite a lot. And you also got water vapor kind of falls in that category as well, because water vapor, carbon dioxide, and methane are the three most potent greenhouse gases. The issue with them is that if you watch the news, you'd think our air is filled with carbon dioxide. It's actually a very small percentage. It's only 0.037, and the reason it's gets so much attention is actually because the number is so small. Even a small change in that percentage can have a huge impact on the weather and the climate. So if it was the percentage that oxygen is, a small change of sort of 0.005 wouldn't have much impact, but because the number here is quite small, a percentage change from 0.005 would have a huge impact. And if you just have to look at Venus to see what it can lead to, because Venus has a runaway greenhouse gas effect caused by too much carbon dioxide. Anyway, moving on. So this is the practical we would use in order to identify the percentage of oxygen in the atmosphere. I've got two gas syringes, got another syringe, and in the syringe you've got some copper. I would normally start this syringe at 100. The only reason is it's very easy to calculate the percentage then. So if that's at 100, you're expecting it to go down by 21 centimetres cubed because that's 21%. And what we're going to do is we're going to gently heat up this whole surface. We're going to wave it across because the whole thing needs to be sealed. So if I heat in one place, that's going to melt the tube and oxygen and the air can get in, which will affect our results. So I'm going to gently wave it across, but I'm going to heat up the copper. And when you heat up the copper and you put it in oxygen, it reacts with the oxygen to form copper oxide. So my gas is now turning into a solid, which means that the gas is being taken out of this. And as that gets taken out, this is going to reduce the volume. So as I heat it up, I'm going to push this syringe in, which is going to push this one out. Then I'm going to go back, and then I'm going to do it a few times. Now, there are three areas where this goes wrong. Okay, the first one, when people calculate, they forget to include the volume of this tube. So the oxygen in this tube will also be taken out, which will affect your results. The other thing is you need to take the heat and allow it to cool. Air expands, which means the volume will increase to start off with. When you let it cool, it will then shrink, which will cause this gas syringe to go back in, which will make the measurement hopefully 21 centimetres cubed. So you do have to be aware of that. The last thing is that all the copper, or you need enough copper to make all the oxygen react, which is quite a bit. If you use something like copper turnings don't have a very high surface area. You want something like copper powder. Copper turnings will react, but because the surface area is quite low, it won't react with all the oxygen. So you need to make sure you have got excess copper, otherwise all the oxygen won't react. Another way of doing this practical is something that looks like this. And if you take this, which is a boiling tube, and you turn it into a measuring cylinder, it becomes a bit more obvious. You fill this up with air, so it must have air all the way down to the bottom, or the 0 mark, which is actually normally about there on a measuring cylinder. You put some iron wool in, and the oxygen over time will react with the iron wool. That will remove oxygen from this bit, and it will suck the water up. There's a couple of problems here. Firstly, you have to account for the volume of the iron wool, which isn't always easy, because that will take up some of it. So that has to be included in the calculation. You won't have, if you put this at 0 and it's 100 centimeters cubed, or you put it at 100 centimeters cubed down here on the measuring cylinder, some of that volume will already be taken up by the iron wall, and it will still be there at the end. The other thing to bear in mind, you've got gravity, which is pulling this down, and the other thing to bear in mind is actually oxygen can dissolve in water, so that might lose a little bit of the volume. I've also seen this done with a candle. So you put a candle in as well. The candle produces carbon dioxide, and the candle produces carbon dioxide and water. The water goes back into the water. The carbon dioxide dissolves in the water, which does the same thing, but you also have to, same rules, have to account for the volume of the candle.